This lecture is an exploration of how physicists and also chemists and also materials engineers and people who think about sort of atomic and molecular structures for engineering applications. This is how people sort of begin to understand the structure of multi-electron atoms. So previous to this lecture, you would have learned about single electron atoms. For example, the hydrogen atom. The hydrogen atom, when you have it as a neutral atom, has a one proton and one electron. And there is some quantum mechanics that you can do with Schrodinger's equation that basically gives you all of the quantum physics. It does all of the quantum physics predictions, gives you the energy level structure, tells you about the quantization of angular momentum, and then you add in a little bit of extra physics, that's the spin of the electron, and basically you know everything about the internal structure of a hydrogen atom. The problem is when you have multi-electron atoms, quickly the math problem of Schrodinger's equation quickly becomes intractable. You can imagine that if you have even just a 2-electron atom, you've got 2 interaction energies for each electron separately interacting with the nucleus, but then you have a third interaction energy that's actually just between the 2 electrons, right? Because it's not like they ignore each other. There's there's electron-electron repulsion. But anyways, we can actually use a lot of the structure and kind of quantum mechanical thinking that we learned for single electron or hydrogen-like atoms to basically understand what it's going to be like for multi-electron atoms. And so I'm going to start off just by sort of thinking aloud about some of the issues that arise and some of the things you might begin to guess and wonder about. Okay, so let's start here. It says, imagine we have a bare nucleus of Z protons. So when I say a bare nucleus, what I mean by a bare nucleus is it simply is just a nucleus. So I've got a nucleus, it's got Z protons, so that means that the charge of this little thing is Z times E, and notice that it's inherently a plus sign, right? It's a positive charge. Protons are positively charged, right? So if you have this out in the universe, if it's all by itself, it can stay this way. But if there are electrons around, of course, electrons are going to be attracted to this positively charged thing. And so let's imagine adding 1 electron. So I can add this electron actually anywhere. And the interesting thing about that is when I imagine putting the electron on, now I have a, you might say I have a single electron atom, right? And with this single electron atom, we already know how to write down the energy of this atom. The energy, it's, so strangely there's a minus sign, but then there is the mass of the electron. This is Coulomb's constant. It's K is 1 over 4 pi epsilon naught, so it comes in squared. Then there is the proton number Z, right, which is just the number of protons. You always imagine it being an integer. We're thinking of integers bigger than 1, right? So there's the proton number, but it comes in squared. And then the charge, the fundamental charge of either the proton or the electron comes into the 4th power. And then you divide by, there's a twice h bar squared. And then there is the principal quantum number squared, right? So here's what's interesting. And I can put this electron in any value of principal quantum number that I want, right? And the possible principal quantum numbers are 1, 2, 3, up to infinity. But then remember that Schrödinger also gives us other options, right? If we want to describe this particular atom, we're invited to choose quantum numbers that look like this. This is the quantum numbers from Schrödinger's equation. And then there is the quantum number from electron spin. So really 4 quantum numbers. So when I add my electron to this atom, in a sense, I have a choice of how this atom is going to exist with its electron, right? Just based on my choice of the 4 quantum numbers. Okay. So once I choose an N, I can choose an L, and L can take values 0, 1, all the way up to N minus 1, right? So your options for L are guided by what principal quantum number you've chosen. And then the options for M sub L are actually guided by the value of L that you're using. So the options for M sub L can be from negative L up through 0 up to L in integer steps, right? And then the options for M sub S, you always only have 2, either plus a half or minus a half, right? Because the orbital angular momentum of the electron spin is spin half, right? It's L equals to 1/2. So anyways, yes, so these are my choices for 1 electron, right? Adding 1 electron in. And it's actually quite simple. But as soon as you get 2 electrons, right? Add a second electron. The first thing that changes is the energies. And the reason is because now if I add another electron, right, these 2 electrons have repulsion between them. That's a little part of the energy of the atom. And then each electron is attracted to the nucleus. So that's 2 other energies, right? So the energy is more complicated. So we cannot use this expression without imagining making alterations, right? So and actually I hate making this mistake, but really, oh no, I didn't quite make the mistake. So, right, this right here is the energy, it's the internal energy of an atom system, right? Which includes, well, for this simple atom, it's simply just, right, single electron. It's just the interaction energy. That's the only energy, well, and also the kinetic energy of associated with the motion of the electron, right? So those 2 energies, the interaction energy between, right, the attraction energy, as well as the kinetic energy of the electron, because we imagine the nucleus standing still, it's so massive. Yeah, so those 2 energies combine up to be this thing I've written right here. Okay, but of course, whenever you have 2 electrons, the internal energies of our atoms become more complicated, right? It's more complicated. Doesn't mean it's not solvable, or approximatable, it's just very complicated. And so that's something I'm not going to write down. But what I am going to do is wonder, if I have a nucleus, I start off with it bare, and then I invite 1 electron to come and live close to this nucleus. So I begin to make an atom system. What are my options if I want to add a second electron, right? I'm building up, I'm imagining assembling on my way up to a neutral atom. So a neutral atom will have the same number of electrons as I do protons, right? That'll be electrically neutral. But in order to assemble this atom, I need to simply just have the situation of imagining 2 electrons, right? So here's an electron and here's an electron. So here is something super interesting. As soon as I imagine adding the second electron, there is a new piece of physics. There's a new law that you have to learn how to obey. So when you add a second electron, its quantum numbers cannot be the same as the other electron. And this is actually a statement that's associated with what's known as the Pauli Exclusion Principle. And this is a really important principle. So the Pauli Exclusion Principle simply says, or one way to say, like one useful way to say what the Pauli Exclusion Principle says is no two electrons in an atom. So we're talking about a single atom, and we're talking about picking two of the electrons in the atom, right? So yeah, so no two electrons in an atom can have the same quantum numbers. This is a big deal. And essentially the principle, right, the statement of the principle, no two electrons in an atom can have the same quantum numbers, that's the statement of how you use it. And the way that we're going to use it is we're going to imagine as we build our atom, as we invite a second electron in, we're just going to remember the fact that the two electrons are not allowed to have the same quantum numbers. That doesn't mean that they can't both have the same n value. So here's an example of two different sets of quantum numbers that have the same n value. Let's say that the n value is 1, right? So this is the lowest energy shell value. And let's say the L value, right? We only get one choice of L value because remember that L takes values from 0 up to 1 less than n. So if n is 1, then n minus 1 is 0. So the only option for L is 0, right? And then m sub L, its only value that we can have is 0. So all of a sudden it seems like the n equals to 1 quantum number choice is so restrictive that it looks like there's only one set, right? One set of values for the quantum numbers, except for the last quantum number, right? The last quantum number, the spin quantum number, or the z component of the spin angular momentum of the electron, can either have the value plus 1/2 or minus 1/2. And so the way that this is often described is, remember that L equals to 0 is an s orbital, right? So what we're going to say is the following if we say that our two electrons have quantum numbers 1, 0, 0 plus 1/2 for one of the electrons, and 1, 0, 0 minus 1/2 for the other electron, we say we're good. We've got two electrons in an atom, and their quantum numbers are different, and we are obeying the Pauli Exclusion Principle. All right? So, and actually, this is how people imagine putting the atoms together, right? Another thing we could have done is, let's start over. We've got Ze. Here's our bare nucleus, and now we invite one electron in, but we give this electron the quantum numbers. I'm just going to make some up. So let's say n equals to 2, L equals to 1, m sub l equals to -1, and the spin is 1/2 with a positive. And the other electron, let's invite a second electron in. Let's put it in n equals to 3 with L equals to 2, M sub L equals to 0, and the spin also up in the z direction, right? This is possible, but you notice that n equals to 2, that indicates that in a sense I've got a lot of energy associated with this electron on the right side, and n equals to 3 indicates that I have even more energy sort of devoted to this electron on the left-hand side, which means this is a this is a very energetic atom system, right? I'm up here in the high principal quantum numbers, so I have a lot of energy. This situation, right, of an atom, so I've got this atom you can see on your screen, is a higher energy system than this system that you see on your screen. Actually, this system here, where both of the electrons are in principal quantum number n equal to 1, this is actually the smallest possible energy for a 2-electron atom, right? It's the smallest possible energy. So if this is the smallest energy, this is called the ground state, right? And this state here is an excited state. We could say it's the very same atom, except for somehow it's absorbed a bunch of energy. And it may later go through some set of emissions of photons. So it'll emit a bunch of photons and again look like this, right? All right, so this is some excited state. So let me type some stuff real quick down here, and yep. Okay, so when we imagine building an atom from a bare nucleus, we imagine adding electrons to the atom starting with the actually, when we imagine building an atom from a bare nucleus, we tend to imagine, I'm so sorry so let me do this, tend to imagine building our atom in the lowest energy state. So in order to do this, right, you start with n equals 1, then move into higher n values, right? And that's, yeah, this right here is the heart of how people sort of came up with a way to describe the ground state configurations of multi-electron atoms with what's referred to as spectroscopic notation, right? So as an example, right, spectroscopic notation. So check this out. So up here, I just did a 2-electron atom, right? So here is the 2-electron atom. And you can see that n equals to 1 for this 2-electron atom, because I can fit both electrons in the n equals to 1 shell, which has L equals to 0 subshell, M sub L values of 0, but the spin can be either up or down, right? So we make one of the electrons occupy the up state, and the other electron occupies the down state. And that ground state, in spectroscopic notation, right? So a 2-electron atom in the ground state, in spectroscopic notation, we say is 1s2. So the 1 is n equals to 1. The s means L equals to 0. And the 2 means there are 2 electrons in the n equals to 1, L equals to 0 configuration, right? So this is called spectroscopic notation. And in fact, actually, there's a pretty cool list in, so the book that I'm about to quote is volume 3 of OpenStax, University Physics, right? Which is the physics textbook that I'm using for the class I'm teaching. And let me show you a page out of that. So I've got it on my web browser. So this is, right, you can see up in the upper left-hand corner, University Physics, Volume 3, Exclusion Principle in the Periodic Table. So in particular, what I want to show you is this. Or actually not that, this. So helium, let's see if you can see the little dot. Helium is He. It's the second row under the element column. And the electron configuration, this is the spectroscopic notation of the ground state of a helium atom. Helium has Z equals to 2. It's a 2-proton nucleus. And the ground state electron configuration is known as 1s2. That's what I just wrote, handwriting for notes. Helium is a 2-proton atom. Lithium is a 3-proton atom. So how can we see that? If we go onto a periodic table, so here is the periodic table, right? Here's hydrogen. Helium is far over on the right at the top, He, right? And then lithium is the next atom. So what we do is we start in the upper left-hand corner, and we first go along the row as far as we can. And then when we finish going across the row, which ends at helium on the first row, we go to the second row. And then we go to the right as far as we can. So it starts at lithium, goes to beryllium, boron, carbon, nitrogen, oxygen, fluorine, neon, right? And what you can see is interesting. You can see the spectroscopic notation on this periodic table. So the first hydrogen is, the first element has a tile. It's hydrogen. It's 1s with 1 electron. Helium is also 1s, and it should have 2 electrons. And then lithium now has a ground state that's 2s, but with 1 electron, because lithium has 3 protons. Beryllium is 1s with 2 electrons, right? And you can see that, you can kind of see the spectroscopic notation. And the idea here is, remember I said that you want to imagine building up your atom by starting with a bare nucleus, right? But the point is as you add electrons to this bare nucleus, you always add the next electron into the next lowest possible energy value. So for lithium, like if I wanted to imagine building up nitrogen, I'd first have to add the 1s. I'd have to add another electron to 1s to make it look like helium. And then I'd add a 2s electron to make it look like lithium. and then I'd add another 2s electron to make it look like beryllium. But now I get to explore non-s subshells. I can have L equals to 1, which is the p orbital, right? So boron, I put an electron, the next electron in, and now it looks like boron. If I put another electron in, it'll look like carbon. If I put another electron in, it'll finally look like nitrogen. So if I look at the spectroscopic notation of nitrogen, let's go up and look at spectroscopic notation of nitrogen, right? So nitrogen is capital N. It's in between the carbon and the oxygen. And you can see that first we added up to the ground state of helium, that's 1s2. And then we added up to the ground state of beryllium, right? 1s2, 2s2. And then we had to add 3 electrons into the 2p orbital. N equals to 2, and then L equals to 1, right? P is N, L equals to 1. And I had to put 3 electrons there. And you can see that what's interesting over on the side is it looks like the way that the electrons are getting paired up is you have an up and down, right? Which is actually just the 2s2. It's actually just the 2s2 being drawn. And then you've got 3 lonely electrons. So none of the electrons are paired, is what they say. Each of the electrons stands alone. So each gets an up arrow. Or they could have been an up and a down or something, but they just sort of default chose up in the z-axis for the spin of each of the electrons in the 2p subshell. All right, so yeah, so all right, I want to show you something interesting though. I'd like to show you, let's look at manganese. Do you see this Mg here? So manganese has a full n equals to 1, right? So we finished filling out all the possible n equals to 1 quantum states, right? Quantum number configurations. And then we actually finished filling out all of the n equals to 2 configurations, right? So n equals to 2, L equals to 0 is the s orbital, and n equals to 2, L equals to 1 is the p orbital. And we finished them, and now we have the 3s2 orbital, so manganese. Manganese actually has 2, yeah. So, all right. So let's go back to the notes. So I showed you that manganese, in order to get manganese, so manganese, sorry, once again, let me go back. And so so manganese is, actually, let's go this way. So manganese, Mg, it's over here, it's the third row, second column. It's 3s, right? Okay, so if I count it up, it's a proton number. Hydrogen's 1, helium's 2, lithium's 3, beryllium's 4, 5, 6, 7, 8, 9, 10. Neon has 10 protons. Sodium has 11. Manganese has 12. So manganese, manganese is Z equals to 12. So neutral manganese in ground state, so the lowest possible energy level, we fill n equals to 1, right? So we have electrons occupying all the possible quantum number combinations that have n equals to 1. N equals to 2, we fill it. At n equals to 3, we can't fill it, right? It only fills the s orbital, but not the p orbital. And so the configuration, right, it's a full n equals to 1. So 1s2. That's how you fill, right? Because we're in n equals to 1, the orbital angular momentum quantum number L cannot have a value bigger than 0. So we're done with n equals to 1. N equals to 2, though, you start by filling the S, and then you finish by filling the P. And P comes with 6 different quantum numbers, right? And then we go and we fill the s orbital, and now we're finished. This is manganese's ground state, or it's actually neutral manganese ground state, because I have the same number of electrons represented by this spectroscopic notation as the number of protons. Okay. So what I think is kind of cool about this is, check this out. I'm going to isolate this stuff in red. So you see it's 1s2, 2s2, 2p6. Let's look at what's in red in the textbook. So in the textbook, manganese, remember, is the third row. And what I was just describing is actually neon, right? Neon, if I go look at spectroscopic notation for neon, is, so here's neon down here. It's capital Ne, 1s2, 2s2, 2p6, right? And that's what I just outlined in red. And this actually offers a really nice, sort of tidy, efficient way to do spectroscopic notation. So here is the neon ground state electron configuration. And to finish, I'm just going to tack on the fact that we also added 2 more electrons in the n equals to 3, L equals to 0 shell, subshell. Right? So we might say this is a noble gas, right? And then this is a few extra electrons. And this actually is kind of telling. This is pretty cool, because you can actually sort of imagine this. So what we imagine is we have neon, and then we add 2 little electrons. And these electrons, if you think about it, these valence electrons are, in some sense, shielded from the full nuclear charge by the inner electrons. And so these 2 electrons out here, they sort of, in a sense, see a reduced nuclear charge. And what I'm speaking to is thinking about the internal energy of this manganese atom, this neutral magnesium atom. Mg is magnesium, I think. I'm embarrassed. I'm going to look it up real quick, just because I'm on the internet and you can watch me. So let's look up, actually, well, I'll leave it to you to go figure it out. That's pretty easy. I admit I'm an unpracticed periodic table of elements reader. I think it's magnesium. Yeah, because yes, I think it's magnesium. Yeah. Okay, so Yeah, so this is an introduction to spectroscopic notation, thinking about how do we understand the sort of quantum numbers of multi-electron atoms, and how similar it is. Like, we're essentially recycling the quantum numbers. We're recycling the quantum numbers that we got from the hydrogen atom. So even though there are other electrons around, we're imagining that we can still add electrons into hydrogen-like quantum number sort of states. Except for we don't have full freedom to do that. We have to obey this very special principle. And if we do this, though, if we obey this principle, we actually generate, you might say that the Pauli Exclusion Principle and the hydrogen atoms, like the Schrödinger equation model of the hydrogen atom gives us these quantum numbers. If you add in spin, the Pauli Exclusion Principle, you can predict the periodic table. Yeah, so the reason the periodic table of elements looks the way it does, and the reason why the various different kinds of atoms participate in chemical reactions the way that they do, is based upon the Pauli Exclusion Principle and the Schrödinger equation, and also this really interesting extra thing called the electron spin. Okay, so in a following video, I'm going to describe something that I don't really understand that well, because, well, I'm going to say that it's a chemistry issue, but really at the heart of chemistry is a bunch of physics issues. But this is something of a fine point. Yeah, so I'll do that in a following video.